This is just a starter problem right here. Just in the starter problem, in my head, I did it wrong already. I simplified it, even though I don't think it can be. But if I would have read the problem, then it would have gone much better, because it says identify the numerator and denominator of the fraction. So that's all we got to do on this one. And so the numerator in the fraction is just the top number, and then the denominator is the bottom number. Now, this is the way it would work if we were back in, I think, module 2. The problem with this one is the negative. So students say, well, if there's a negative right here specifically in the middle with the line, then it just, some students say, and this is an error, they'd say, well, both of these are negative right there. And that's not true. Not both of them can be negative if there's only one negative. Only one of them can be negative. So if we see a negative like we do there, then it's, what we usually do is we apply it to the top number, the numerator.
Why?
In reality, 5.1, which is what we're doing on this one, it really is just a review of stuff that we've already done, but now with negatives. They're also saying rational numbers. I think it's module 7, maybe it could be modules, I think module 6 actually. Module 6, we're going to actually go into more detail about what a rational number is. But right now, even though they're saying this in the title, I'm not going to be using the vocabulary, hey, look at this rational number today. So our objectives for this particular lesson, I can change fractions forms between mixed numbers and improper fractions, which we've already done. But again, the key today is that we're going to see some that are going to be negatives. And then I can simplify and compare fractions. We've done simplifying and we've done comparing, but again, the extra part of this lesson is that they're negatives. So we have done this stuff before. Types of fractions. We got proper fractions, improper fractions, and mixed numbers. So a proper fraction, this is your old-fashioned, very common fraction, which would look something like 1/2. Okay. The main idea with these is that the numerator is bigger than the denominator, or, no, I said that wrong. Strike that. The denominator is bigger than the numerator, which obviously you can see my verbal mistake there. 2 is much bigger than 1. Twice as big anyways. You could have something like 4/5. You could have something like 2/3. You could have 3/7. See what I'm saying? So these are all proper fractions. Now, as it turns out, we would still consider these proper even if we were to make the entire fraction a negative, like this. So if I made that negative 1/2, we would still consider it a proper fraction. Or even the 3/7, well, negative 3/7, still a proper fraction. Now, even though, like I was saying in the starter, we would say this would technically be -1. Well, 2 is bigger than 1 still. We don't really consider the negatives when we consider whether we're looking at proper or improper fractions. Improper fractions. So this is where the numerator now is bigger than the denominator. So that would be fractions such as, I don't know, 3/2 is a fairly common one. Or, I don't know, you guys give me one. 8/5 would work because the numerator is bigger than the denominator. And again, we could make these negative if you'd like. So 10/6 works. Actually, I'm glad you bring up 10/6 because notice that 10/6, well, hopefully we notice that 10/6 can be simplified. If we don't notice it, that's fine. But it doesn't matter if it can be simplified. It doesn't matter at all. All that matters is that the numerator is bigger than the denominator, and that is it. Now, here's another unique example that we don't really consider too often. But if I looked at a number like 3, it by itself, I may not consider an improper fraction. But if we've seen this before, especially when we've operated with fractions where we need to see the denominator there. So seeing it as 3/1 makes it an improper fraction because the numerator is still bigger than the denominator. There you go. The last type here is a mixed number. So that's an integer. Now, it's saying integer, which, yeah, we've seen integers before. Integers are just like whole numbers, but they can be negative. An integer would be something like -4. Right there.
4 3/4.
Yeah, so that would make it a mixed number now, though, right? So -4 is the integer, and then if it's followed by a proper fraction like 3/4, That now has become a mixed number. That's it.
Yep.
Now another common mixed number, again, I'm just kind of throwing stuff out there, 1 1/2, fairly common. Now, of course, there's an infinite number of mixed numbers, the improper fractions and proper fractions, but yeah, this is just to get the idea back into our minds because we haven't seen this for, I think, 2 modules. And like we've been saying, and it's part of our objective, we need to be able to go between mixed numbers and improper fractions, but you don't go from a proper fraction to a mixed number because your whole number or integer would be 0, which we don't usually write mixed numbers with a 0. There we go. Determine if the fraction is proper, improper, or a mixed number. Now, if I saw a mixed, I'm just going to do the first part here. I'm going to eliminate mixed number. Why am I eliminating the mixed number? Because I don't see an integer or whole value with it. All I see is a fraction directly. So we'll put this in here. Since the numerator is bigger than the denominator, this one is a improper fraction. Boom. That's it. 19 is bigger than 13. That's all we need to see. 19 is the numerator, 13 is the denominator. This one's an improper fraction. So fractions, as it turns out, are the operation of division, which again, I think we've seen before, but in the past we used, so we still have a quotient in here, right? We got the quotient right here, but now, in the past, we said you got a dividend and a divisor. We're not using that vocabulary. We're not using dividend and divisor anymore. We're using numerator and denominator. So if you were to look, a very commonly written division problem would be with the old-fashioned division sign right there. If you were to see that, even though it's not written as a fraction, you could make 12 the numerator, and then you could make 2 the denominator. That's it right there. And in fact, which I think we saw in that last exam, is sometimes we need long division like this. The 12 is still in the numerator, even though it's written with long division, and 2 is the denominator. So however you want to look at that, and then of course the quotient would have been this portion of the long division right there. But just to take us back a little bit, the numerator tells us how many parts there are, and the denominator tells us how big the parts are. And I'll demonstrate this here with some technology, which is really just meant to hide how poorly I draw with my freehand anyways. So if this is a pizza, because I like pizza, is this a bad time to talk about pizza? So if I were to look at this shape right here, this circle that I've drawn right there, and I wanted to consider this as a fraction. So in the past, what we did, we looked at these and we said, look, how many shaded pieces are there in this circle right there? You'd say there's no shaded pieces. Okay, so again, that's the numerator that tells you how many parts there are that, in this case, are shaded. Okay, how big are the pieces? Well, there's only one piece in the whole pizza. It's just one pizza. It hasn't been cut. So it's 0 pieces shaded in this pizza. I don't know why you'd shade a pizza. But it's 0 pieces shaded out of 1. Now, if we were to take this, so let's take this shape and see if we can play with this just a little bit. You know, let's say that I did, because I would consider this kind of a small pizza. Let's make 2 cuts right here, right? And let's start shading some delicious goodness. Again, maybe I shouldn't be doing that because of the time of day it is, but yeah, and then staying between the lines is not my forte. But in any case, I would look at this one and say, how many pieces are shaded? Now there's 2. But again, the sizes of the pieces, that's the denominator. So we used to have 1 full piece, but now how many pieces are there? So the sizes of the pieces are in fourths, which is the denominator. So there's 4 pieces that make up the entire pizza here. 2 of them are shaded. 2 is the numerator, 4 is the denominator. So when we see fractions like this, especially the denominator is crucial, because if I have 4th size pieces, and this again just takes us back to what we've seen before. If I had another pizza right here, and it's not the same color for some reason, but let's say that I cut this one into, let's say, 6ths now, right? Like this. So this new pizza that I have is now cut into 6ths. And let's do some shading in here. Trying to make it look real pretty. Let's do these 2 right here. Okay, so I've got 2 pieces out of 6, and then I've got 2 pieces out of 4. A common error that students make is they say, look, I've got 2 pieces and 2 pieces, that's 4 pieces. That's true, you have 4 pieces. The problem, not the same size. So that's why when we start adding and subtracting with fractions, again, which we will do, it's important to know that you need to cut both pizzas, the same size pieces. Because if you don't, then you're adding not the same size pieces. You have 4 pieces of pizza, but again, you don't have the same size. And that can cause problems, especially in a party when people are trying to get the same amount of pizza. I try to just take as much pizza as possible, but... So here we go. Here's our first example. If the big rectangle represents 1 whole, what fraction of it is... I read that wrong. What fraction of its area is shaded red? Okay, so let's set up a fraction right here. Here's our fraction. So yes, the numerator is 6. There's 6 pieces that are shaded red. And then you got 6, 7, 8, 9 total pieces. So they're 9th size pieces. Now, this is not a circle like the couple examples that we just looked at before. That's okay. It's still in 9th size pieces because really we would look at this whole, and I know I'm not really following the lines there, but that makes up a whole, I want to call this a candy bar because if it's rectangular, that's just the way that I think about it. I don't know. Some people like to think of it's like bubblegum pieces. I don't know, whatever. And now, again, I'm getting a little ahead of us here, but 6/9 can be simplified, but we're not worried about simplifying right now. We just want to know what this fraction is directly. That's it. Would I make a mixed number out of this? Yeah, we cannot make a mixed number out of this because you have to have more than one full, whatever this is, rectangle, in order to make a mixed number. If we were to look at this example, just right off the bat, now it says what fraction and mixed of its area is shaded. So yeah, I guess we're going to do it in both formats right here, but yeah. So right here, just like we were saying on the last one, I see 2 full circles shaded, fully shaded circles. Which means that I should be able to put this into a mixed number. Instead, we're going to put it into a mixed number as well. Okay, so we definitely have 2 full pieces. Right here, you got 1 full circle, and then you got a second full circle, 2. And then you got 1, 2, 3, 4 pieces that are shaded in cyan, I guess. That's 4, 5, 6, 7, 8 total pieces. So that's 2 and 4/8. Now, that is our mixed number right there. Okay, now you can count each individual one, but first for our improper fraction. So yes, on this one, I have just an individual fraction. I'm not looking for having the integer or whole number attached to the proper fraction. Well, improper fraction now. But what you can do, as you can see, look, I'm just going to count these up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, boom. 20 shaded cyan or cyan pieces. And how big are the pieces? Well, they're still 8th size pieces. So the 20 is usually where students can get. But a common mistake here is where they say there's 24 total pieces, which there are, but that's not the size of each piece. They're 8th size pieces because there's 8 pieces in order to make each individual circle, I guess. You can use this, I call it cycle method, which we're going to see today. You could have done 2 times 8 plus 4 and still got the 28ths, but. All right, so fractions can be written in different ways without actually changing the value. And this is something that I wouldn't say that students struggle with. It's just sometimes it's kind of hard to understand. Now, this goes back to in the classes that I teach, we say, what is it that you want out of the fraction? Maybe 5/8 is not actually what you want. And there's reasons why you may not want it, which we'll get into later. The main thing about looking at this fraction, 5/8, is that maybe the 8 is not the denominator that we want. Maybe we want like a denominator that's 16 or 24 or 80 even, who knows? But what I can do is, if I were to look at we'll call it a pizza. Oh, that's not what I wanted. Let's go with this one right here. There we go. So let's say that's pizza. Let's pretend like I'm cutting this very nicely into equal sized pieces. It's not my worst. Anyways, so we'll say we got 5 of these pieces. There's 1, 2, 3, 4, and then I got a 5th piece right there. Boom. Okay, so I got 5 pieces out of 8. Now, for some reason, maybe instead of 1/8 size pieces, maybe I don't want 1/8 size pieces. Maybe I want smaller size pieces, which we may end up wanting. So in that case, I would maybe I'm going to cut these in half right here. Now, I know that's getting really sloppy, but what I just did there, and I'm not going to count these, but I just made it 16 pieces, and now how many shaded pieces are there? There's 10. Did I change the size of the pieces? I did. Did I change the size of the whole pizza? I did not. So I can change the sizes of the pieces and still say I have the same amount of pizza. So that's what we're looking at on this. Now, if someone were to ever ask me, just find some kind of equivalent fraction of 5/8 right there. A common thing that students do is they say, I'm just going to multiply it by 2 because 2 is a fairly easy number to multiply it by, which is essentially what we did right there. We took the 5/8 and we said, you know what, I multiplied this by 2 and 8 by 2. If you do it to the numerator or denominator, you got to do it to the other one as well. Okay, now if I were to see this fraction 5/8, like I said, I like to make this as easy as possible, and 2 is fairly easy. It's like 5 times 2 is 10, and 8 times 2 is 16. But, especially if I don't have to draw it, which I'm not going to, the easiest number that I can multiply by is 10. So that's like taking the 5/8 like this and just being like a 50/80ths. Boom. And it's still equivalent, but it is not exactly, it doesn't look the same, but it is. All I did is attach zeros on there. And some students are like, well, how many zeros can I attach? Well, as long as you attach the same number of zeros to the numerator and denominator, you can do it as many times as you want. If you're trying to make denominators the same, generally you will use multiplying. The division comes in if you're ever trying to simplify. So that would be like, so again, I'm gonna break off here and just, let's take an example. Let's take 4/6. That seems fairly simple. So we would say, can I simplify this? Because down here, well, at the bottom, we multiplied by 2. Here, what we would say, you know what, we can divide both these by 2 this time. And it will give me an equivalent, a fraction that has exactly the same value, but it will look different because now 4 divided by 2 is 2, 6 divided by 2 is 3. And so these 2 fractions that I have up here at the top right here, 4/6 and 2/3 have exactly the same amount of pizza. They're just shown differently. The sizes of the pieces are different, but overall you still have the same amount of pizza. All right, so changing mixed numbers into improper fractions, I use what I call cycle method. Is there an actual formal name for this? Not that I'm aware of. And I've asked other professors about this, but cycle method is the method that I use. Now, when we change a mixed number like this into an improper fraction, which is what it will turn into, so it will be equivalent, but what will happen is your denominator will stay the same. So you could automatically start out by just writing the denominator, whatever this is. Now it's showing as a letter. Usually that'd be a number. Like if this was 5 right here, I could automatically just make this a 5 right here.
Yeah, it stays a 5.
Correct. None of this cycle method is ever going to change your denominator. Now, once you get it changed into an improper fraction, you may need to do some simplification.
Yeah.
But now, here's the thing too, is if it can be simplified, then it wouldn't be technically in a formal mixed number format. But I don't trust math people enough to say that they won't do it to you. So just be aware, okay? So this is saying A times B plus C right here, right? So why is this happening? Okay, so on this example that we saw with the circles right here, right? This was 2 and 4/8 right there. Now that is not technically formal mixed number format because the 4/8, well, I guess you could say it is, but the 4/8 can be simplified, whatever, all right? Now, with this, what we did is we changed this into a improper fraction of 20/8. So again, notice the sizes of the pieces are not changing, which is what we're showing here. But why is it that you do 2 times 8 right here? It's because you got 2 groups, 2 full pizzas that are 8 pieces each. So there's 8, 16. 2 times 8 is 16. So in this process, we would say you'd do, in this cycle method, you do 2 times 8. That's 16 pieces. That's these 8 and then these other 8, which is 16 total pieces. And then you add the numerator, so 16 plus 4, and that would have given you the new numerator of 20, which is right here, 20. Okay, but where did those 4 pieces come from? That's these 4 right here. So that's why cycle method does work. And it's a lot better than drawing pictures all the time, because sometimes they're going to be like, do it in ninths, and I don't know how to cut pieces into ninths. I can do like halves and fourths and eighths. But you saw once I got past 8, it was pretty ugly. So write the mixed number as an improper fraction. Try this one out. 1 minute. So cycle method on this one. So like we're saying, with the end fraction, I can apply the negative now, or I can apply it at the very end. It doesn't matter. Just make sure you don't forget to do it, because if you don't put it in there, you may lose credit. And like we've seen, some of these types of problems are just like 1 point, and if you miss the negative, it's like all the credit's gone, even though you did all the rest of the work. So on this one, I would say let's do 20 times 7. Now, if you can do 20 times 7 in your head, that's pretty good. But let's say that we've forgotten how to do that. So right here, I do the multiplication. And notice I'm not worried about the negative. I've already applied it to the answer. So I'd say 7 times 0 is 0. Then 7 times 2 is 14. So that's the multiplication part from cycle method. Then I'm going to finish cycle method by adding the numerator. So that 140, I'm going to add the 4 right there. And that will give me the new numerator. 0 plus 4 is 4. We'll drop the 4. We'll drop the 1. 144 is my new numerator. The denominator, which used to be 7, and I could have applied it already, but I forgot to. But I haven't forgot it yet. It's in there. That's my final answer. Negative 144 sevenths. And that is it. Let's say that, because I have that negative just kind of where that the fraction line is in the middle. But let's say on a test you were like, you know what, that 144 is negative. It's still full credit. All right, mixed numbers and improper fractions. This is where we're using long division, which we saw already. So long division, we use this symbol or operator. It's the division sign. It's just written in kind of different way. And this is where we're going to take the numerator, and that goes inside that symbol. And then the denominator is on the outside. We want to know how many denominators go into that numerator. The result of this is going to be your quotient. That's your quotient right there. And then after the work down here, you should end up with some kind of remainder after doing, there's usually maybe a few lines in here where you're doing some subtraction, but at the end, we have a remainder. We have a quotient and a remainder. In this setup, so there at the bottom, that's a remainder. Okay, so it sets up like this. So you start with some kind of improper fraction. You're going to end up with a mixed number. Now, the denominator, whatever it is still going to be whatever it is. You still have a denominator right here. But in the mixed number, your quotient is going to be the integer or the whole value in front of the fraction. And then the remainder is the number that goes in and becomes your new numerator. All right, so let's do this one. Now again, I'm expecting a mixed number, so I'm going to put my fraction line in here, and I'm going to put my negative in there already, just so I know that it's in there, and I don't have to worry about this negative ever again, because I don't have to. But what I do have is a division line right here. The fraction line is a division line. My numerator is 50. It's not a very good long division line sign, and the denominator is 9. So it's 50 divided by 9. This actually reads 50 divided by 9, even though it's not in order from left to right. Some students say this is 9 divided by 50. That's incorrect. Now, if you say that to most math nerds, they'll freak out, and it's not very pretty. But just be aware, this is not 9 divided by 50. It's 50 divided by 9. I don't really care, if we make that mistake, because we just make mistakes, and that's okay too. All right, so the long division here, just going back to what we've seen already, we would say, how many 9s are in 5? Well, I can't think of any. 5 is not big enough, for 9 to go into. There's no 9s in just 5 by itself. And so from long division, just to go back again, this means we're working from left to right by place value. If I don't use a place value, then I've got to look to the next place value and combine the two. So now I am looking at this as 50. How many times does 9 go into 50? Well, that would be 5 times, right? Yep. 5 times 9. Now this is where we go back. Say, well, 5 times 9, that's 45. So we started with 50 pieces to divide amongst 9 people. I don't know. I think of like, money's always good. So you got 50 bucks, you're going to divide with 9 people. Well, if that's the case, we have enough to give everyone 5 bucks, but that you only use up 45 of the bucks. So if I take that out, then I have what we would consider a remainder, and then we'd do some subtraction there. 10 minus 5 is 5, 4 minus 4 is 0. So if this was the case, if I said I've got 50 bucks, I'm going to divide it with 9 people. Every person gets 5 bucks, but then we have a remainder of 5 bucks. So the $5 in green, which is our quotient, that's the whole number. The remainder is the numerator. And the denominator, which used to be 9, is still 9. And that's it. Now again, I had already put the negative in there, and I waited till the end to put the denominator, even though I could have done it from the beginning. It doesn't really matter as long as you put it in. And also, I've tried to color code these two 5s because they are the same, but they do not represent the same things. So we need to keep that in mind. The quotient, if this was a 6, I'd have a 6 here, right? Well, negative 6. And if this was like a 7, then I'd have a 7 in the numerator. And it's important to understand the difference between those two. All right, here we go. We're going to plot these values on the number line. We got negative 1 and 1/4. We have 3 halves, and then we got 2/3, which almost look the same, but they're different. So take a minute. Try to plot these on the number line. We got 3 different denominators on this, and that's not a problem. We'll show how to kind of work that out. Let's start with, we'll go from left to right. So we got negative 1 and 1/4, and the good news is that each unit, so there's 1, there's 1, there's 1, each divided into 4 parts. So these are 4th size, increments. 4th, 2/4, 3/4, 4/4. There's 1, negative 1, or it works in both directions. So the negative 1 and 1/4 of the 3, I would say, is probably going to be the easiest. So we'll do this one. We'll do this one in blue right here. Okay, so negative 1 I know is right there. And since each of these markings is its own 4th, now notice I'm at negative 1, right, which is to the left of 0. That's important because we are in the negatives from the negative sign right there. But I need the extra 4th right here, right there. That's going to be negative 1 and also an extra 4th. So I put that marking there. Of course, it would be like a dot on the assignment, like that. Okay, so that's negative 1 and 1/4, which it's very nice to have mixed numbers when we mark these on number lines. So seeing something like 3 halves is still okay. The problem here is that my halves, the halves are, these are in 4ths right here. That can be kind of problematic. So even though they're split up into 4ths, what I'm going to do with this 3 halves, which I will do in red, is I'm going to say, look, I'm going to have to cut each of these into halves. So instead of this being in 4ths, I'm going to look at this as that's 1 of the halves. This would be 1, which is also 2 of the halves. And then I would have to go to a 3rd half, which is the value that we want. So I'm going to put a dot right there. Now this means, since I put this in half, right? So let's look at this half mark right here that I put in red. That was from 0. I went 1/4 and 2/4, which is the same as 1/2. Now, did I need to know that? I didn't, because I just needed to say, pretty much what I did is I kind of ignored those markings, and then I put my own 1/2 mark, which just happened to align with 2/4 as well. So you can look at it that way if you'd like. It doesn't really matter. It's going to give you the same answer right there. The next one, let's do this one in green, 2/3. Now, that's 2/3. The increments are in 4ths, so I can't even use the marks that they've given me, other than to kind of estimate on this. So again, what I'm going to do is I'm pretty much ignoring any of the marks in between 0 and 1. In fact, let's clean this up a little bit just so we can see each marking, or between 0 and 1 at least. So if I had this, because I am going to have it in thirds, I would need 2 marks between 0 and 1. There's 1/3, and then I'm going to call this, that didn't come out very well, like 1/3 right there, and then, let's say that's 2/3 right there. My increments may not be exact, but that's okay. I'm doing it by hand. So, and then of course 1 by itself would be its own 3/3, and we can give these markings. Oh, what the heck? Come on, technology. There you go. So this is our 1/3 mark. That's 2/3, and then again 1 by itself would be 3/3 right there. But we have 2/3 in our marking. Is that exact? It's not, but we're going to pretend like I'm really good at it. So that's where I'm going to put my mark. And again, even though it doesn't align with the fourths or even the halves, that's okay. We had to make our own mark, no problem. It would be approximately be right there anyways. So my mark may not be exact, but it's close. All right, on this one, we've got 2 markings. We've got B, which I guess I'll do in red, and then A we will do in purple. Okay, now, on number lines, it is crucial to know where 0 is, and I'm going to kind of emphasize where 0 is with this black line. Why is 0 important? It's because 0 is where the numbers are going to change from negatives to positives from left to right. So everything to the left of 0 is negative, everything to the right of 0 is positive, which we should have went over, I think, in module 4? 3, probably 3. Either way, hopefully we've seen that before. So what we have, though, again, we're going to make fractions out of these, and I don't see either of these being bigger than 1. Either B, for example, is between 0 and -1, and A is between 0 and 1. So these are both going to be proper fractions because we don't have enough to make a whole, right? Now, I like to work from left to right, so I'm going to do B first. But I need to know how many pieces make up a whole. So this would be 1, 2, 3, 4, 5. Now here's the thing, is I counted 5, so that means for B I'm looking at fifths right here, some number of fifths. Now it's going to be negative, and we'll get to that, but I'm going to point this out because it's a common enough mistake. Some students just count these lines right here in between the 2 units. There's 1, 2, 3, 4, and they say there's fourths. That is not fourths. In fact, that would be 4/4 right there, which would be weird because it's not 1, or -1 in this case. So we need to count the line that also makes up the full unit right here. Okay, start with 0, 1, 2, 3, 4, and there's 5 pieces. Make sure, because that's a common enough mistake, and it breaks my heart to take credit away on exams when it's like, it's such a small error. Okay, so B though, B, which again we're doing in red, how many fifths is it? That's 1, 2, 3, 4, but it's not 4. It's -4. Now, I put the negative there. Again, some students like it right there. It doesn't matter. It's the same thing. But that right there is B. So, A, notice, and for these, even on the assignment, they're not going to be like, well, on the left it's in fifths, and then on the right it's in sevenths or something weird like that, right? So even right here for A, we could say, I know I'm dealing with fifths either way. In fact, I'll try to make that color code. There's fifths. And you could count again, right? So 1, 2, 3, 4, 5 parts to make a whole one, whatever. And then, A is just the first fifth, 1 of the fifths, 1/5. That's it. So we got 2 strategies for simplifying fractions into lowest terms. Now, on this, it's talking about multiplying and dividing. So multiplication is what you use to make common denominators, which we're not doing right now. We're looking at simplifying, and when you look at simplifying, you're usually looking at division. Division is what we will be using to make lowest terms, because dividing is what makes numbers smaller. We only want dividing with, usually with simplifying. So if you ever see that a fraction can be simplified, you must simplify it, because on an exam, if you do not, points gone, boom. So take your time on these, all right, especially on an exam, and just look at them and make sure that it cannot be simplified. Going back to what we've said already, when we divide, remember that you're dividing both the numerator and denominator. So numerators and denominators have to be divided by the same number. Just like if you were to find common denominators, you would multiply them by the same number as well. With that, though, there's another method, and that's prime factorization. Do you have to use either specific method? You do not, as far as I know. We're not ever going to be like, if you don't use method 2, minus 5 points. Not that I'm aware, okay? So just choose which one that you like the best and then go with that. I tend to use method 1. Unless the number looks really freaky, then I will use method 2. But it depends. And again, is one better than the other? I'm going to say no. Now, prime factorization, what happens is that you're going to start out with a number. Let's take numbers like 10 and 15, because these are pretty easy numbers. Not 50, but 15. There we go. Okay, now, when we say prime factorization, it means that you're going to take the 10, and instead of showing it as 10, because sometimes you want to show 10, or whatever number you're dealing with in a different way. Instead of 10, I'm going to show it as its factors. Factor implies multiplication, so that'd be 5 times 2. 15, instead of writing it as 15, you can do it as 5 times 3, like this. Now, those are both prime factored. 5 times 2, those are both prime numbers. 5 and 3 are both prime numbers. But what we see is a matching 5 in the numerator and denominator, and so some students would say this cancels out, which is okay. But it's not like it just disappears. What happens is it becomes a 1. And what we do is we make it essentially a phantom 1. So it's still there, by the way. It's still lurking in the shadows watching, which is what makes phantom numbers creepy. So just be aware. It's there. It's looking. It's watching. But we don't have to see it anymore. Let's do this both ways. So I'm going to start with method 1. So I'm going to take 12/28. In fact, I like it so much, I'm going to do this twice. I'm going to use this method twice, and I'll show you why here as we do this. So I've got negative 12 over 28. I don't care about the negative. Again, my new fraction is going to be negative again. But I know 12 and 28. Now, some of you may know something that you can divide by something bigger. I'm going to pretend like we're going to start with some basic numbers to divide by, which we should be using to simplify. Now, I'm going to go even lower than that. So you may notice 4 on this, which would be fine. I'm going to go one step below that and say, you know what, I see these are both even, and I'm going to divide them by 2. Now, could you divide them by 4? Of course you could, right? But again, I'm going to pretend like we didn't know that. Then you'd get 6 and 14 right here. Now, because you notice that we could divide 12 and 20 by 4, that means in addition to that, I can take 6 and 14 and further simplify it. Notice I've got my negative, but I could say, I'm going to divide these by 2 again. So 6 divided by 2 is 3, 14 divided by 2 is 7, and then you got negative 3/7. Now, I did it with 2 separate divisions, and that's okay. All 3 of these fractions have exactly the same value. It's just the sizes of the pieces changed, and since the sizes of the pieces changed, the number of pieces that we had changed as well. So what you could have done, and that's what we were saying there before, is so again, I'm going to make my fraction negative. I've got my negative sign in my fraction because I know I'm going to have a negative fraction. But again, just to skip 2 divisions, maybe you like division, I don't know. But what you're going to do is you're going to take both these and say, you know what, I know these are both divisible by 4. How do you know that these are both divisible by 4? That takes memorizing that multiplication table that we saw in the first semester. Now, the division isn't too bad, especially if you have the multiplication table memorized, but 12 divided by 4 is 3. 28 divided by 4 is 7. And what we notice, hopefully, is that both fully simplified fractions are exactly the same. One of these, this one here on the bottom, took less division than the top one, but it doesn't matter. It doesn't matter as long as you get the same answer. And that's the crucial part. These 2 fractions have the same value as these 2, and in fact, this one as well. But again, this negative 6/14 is not fully simplified. So even though it is simplified, this is a simplified form of negative 12/28, but it's not fully simplified, and that's the crucial part right there. Make sure when you get to the end of these fractions of simplifying that you think and just kind of look again, 3 and 7, they're both prime, and 3 doesn't go into 7, or 7 go into 3, however you want to look at that. 7's not a multiple of 3. And so you cannot simplify this anymore, okay? So That's it. That we would consider that simplified. Now that's method one, where you're just simply saying, I know I can divide these numbers by certain values. The other way to do this is to use prime factorization. So that takes negative 12 28ths. And what we're going to do is I'm going to make these, it's still a negative fraction, but I'm going to make, notice I've got that fraction line a lot bigger, longer, so that I can put more multiplication in there, okay? So I'm going to take these two numbers. Let's start with 12. So I got my 12er right here. And then this is where we make a factor tree like this, which hopefully you remember. But I'd probably say 2 and 6. Some students would say 3 and 4. It doesn't matter. We're going to end up with the same numbers. And then 6 would be, we'll say 2 and 3. Now, these circled numbers are the same if they're the prime factors of 12. So that means if I were to take those three numbers, 2, 2, and 3, and multiply them together, I would get 12. Now, again, this goes back to the power of knowing that you can do this with numbers. This is the same as 12. I just don't want to see the 12. What I'd like to see is the prime factors. Factor being multiplication. So that's what I've done. And I'm going to do that also with 28. So I'm going to take my 28 right here. And I say, well, that'd be 7 times 4, or 4 times 7. And then 4 would be 2 times 2. So those are all prime factors as well. So again, instead of, I'm not changing the value, I'm just changing the way it looks. So I'm going to make it as 7 times 2 times 2. Now, I've actually purposely not lined up one of the 2's on purpose. Yeah, so at this point, we say, look, I got a 2 on the top in orange and a 2 on the bottom in blue. They match. You could cross them out as 1, and that's a 1 just slanted like that, because they match. You could do it the same thing with these 2's as well, okay? So if you have a match on the top and bottom, just you get to cross them out, and they become what we call phantom 1s. Now, the 3 and the 7 don't have anything to match, right? So again, I've got a negative fraction, I've got a 3 on the top, and then I've got a 7 on the bottom. And behold, we have exactly the same answer here as we did here and here. Now again, am I going to say that one of these is better than the other? No. But I will say this. A lot of students, when they get enough experience, they don't usually use this method. Unless the numbers are really, really weird looking. But again, you'll never be required to use one or the other. So we got to be careful with these letters because letters in math tend to destroy lives. Well, actually, letters do by themselves, but this is letters and fractions destroy people's lives, which we don't want it to destroy your life. So what we're going to do on this one is, first off, we're going to ignore all the letters. Just look at the numbers first, okay? So in this fraction, we got, we're going to have another fraction on this, okay? But first, let's just look at the 25 in the numerator and the 45 in the denominator right here. If I can simplify this fraction, 25 45ths, then I can just write it into the fraction here, and then I will be done with the numbers part of it. So what I'm doing right now is I'm taking this big fraction, 25a squared b cubed c to the 6th over 45ac to the power of 2, and I'm breaking it up into smaller, more manageable parts, so I don't have to focus on everything at once, which I would like not to do. So I got 25 45ths, and I'm going to simplify this just like we did the last fraction. So 25 and 45, they both have a 5 in the ones place value, so I know they are both divisible by 5, and that should actually fully simplify, but we'll double check. So in this fraction, 25 divided by 5 is 5. 45 divided by 5 is 9. So instead of showing it as 25 over 45, I've just changed it into 5 over 9, and that is fully simplified. I can't simplify those two any further. I can't divide them by the same number or any other number than 1. Now that I've done that, I'm going to focus on just the letters. So let's start with the A's. Well, I guess we'll do it alphabetically. I got a to the power of 2 over a. Now I'm going to rewrite this, but in expanded form. So a to the power of 2 is going to show us a times a, and then we still have the a on the bottom, like this. Now, just like we saw with prime factorization, if I have matches in the top and bottom, I can cross those out, and they simply go away, like this. There's just one of the a's. Now this a, it's important to remember that this a that's left over is in the numerator. It's in the top, so it needs to stay in the top. Because some students, even though they've done that correct, what they'll do is they'll say, you know, it goes on the bottom, and I don't know why they do that, but it shouldn't be on the bottom. It should be on the top in the numerator. Along those lines, if this a that I have right here, if it wasn't on the bottom, then it would have need to have stayed on the bottom. Next up, we've got this b cubed. Now, there are no other b's. So this b cubed right here on the top is just going to stay on the top. That's it. Nothing to do with that b to the power of 3. It just stays where it is. Now, let's look at the c's. And again, we're breaking this up into smaller, more manageable parts. I've got c to the power of 6 over c to the power of 2. Now, we're gonna expand this again. So I've got 1, 2, 3, 4, 5, 6 c's, all being multiplied together. Those are c's. And then I've got 2 c's on the bottom multiplied together. Okay, so again, the exponent tells us how many of the bases are being multiplied together, which we have right there. And I've got 2 c's that are gone. And so in the numerator, I've got c's all multiplied together. There's 4 of them. 1, 2, 3, 4. So I have c to the power of 4. Now, again, I'm just going to emphasize this. None of these letters left over were in the bottoms, but it is possible for that to happen on the assignment. So just be aware, like if these 4 c's were on the bottom, then you'd have c to the 4 right there instead. That's it. But as of now, from what we can see, that is fully simplified as is. Try this one out. 3 to the power of 4 times 7 to the power of 7 times 11 to the power of 5, all over 2 to the power of 2 times 11 to the power of 6 times 7 to the power of 3. Try it out. So on this problem, I'm looking for, well, I'll start with 3 to the power of 4. We'll start with that. So 3 to the power of 4 right there. Now, if it can be simplified, this 3 to the power of 4, there would have to be some base 3 in the denominator, but there's bases of 2, 11, and 7. You got exponents of 3, but not bases. So that 3 to the power of 4, there's nothing to do with it. It just has to stay 3 to the power of 4. Okay? Now I would look next to the base 7 right there, 7 to the power of 7. There is another base 7 on the bottom in the denominator with a power of 3. So let's take a look at that. We got 7 to the power of 7 in the top, the numerator, and 7 to the power of 3 in the denominator. Let's go ahead and write these out. So 7, 1, 2, 3, 4, 5, 6, 7 sevens, all multiplied in the numerator. And then we got 1, 2, 3 sevens multiplied together in the denominator. Now, knowing here that I see more 7s on the top than the bottom, I'm expecting my base 7 to remain in the numerator. I just don't know how many there are going to be to apply the exponent. So I'd say these 7s, and these 7s all become phantom 1s. And then I have 1, 2, 3, 4 7s in the numerator. So it will be 7 to the power of 4 still in the numerator. No more 7 to the power of 3 because these 3 7s became phantom 1s instead. Now my next base is 11. So I've got 11 to the power of 5 in the numerator. And then I got a base 11 also in the denominator to the power of 6. So again, let's rewrite this. I got 1, 2, 3, 4, 5 11s in the numerator, all being multiplied. And then we got 6 in the denominator. 1, 2, 3, 4, 5, 6. Now from this, once again, I see there's more 11s on the denominator than the numerator. So in my final answer, I'm expecting to see that 11 in the denominator of my final answer. I just don't know how many they're going to be, right? So let's see how many there will be. We got 11, 11, 11, 1, 2, 3, 4, 5 of these become phantom 1s. There's only the individual 11 on the bottom, or the denominator. So I can put a 1 there, although you don't technically have to. I'm going to keep it there because I'm too lazy to erase it. Now, the last base I have is a 2 to the power of 2 in the denominator. Well, there's no other base 2s to work with, so it just stays in the denominator as well. I made my fraction line too long, so let's just clean that up a little bit. And now, that is it. So we've seen this already as well. Division by 1, dividing anything by 1 is itself. So if I were to take, and this is true with letters as well, if you had a letter, you could divide it by 1 and you get the same thing back, right? What we're doing here is we're saying, if you took something and split it with one person, not any other people, just one person, how much does that person get? You get whatever you had to split with. So if you have $5 and one person splits it amongst themselves, which sounds really weird, that person gets $5. Or if they had $7, you're going to split it with one person? Yeah, that one person gets $7. So this is called the identity property of division. I mean, that seems more technical than I meant it to be, but either way. 0 divided by anything is 0. So that's this first line right here. If 0 is the first number, which we used to call the dividend, now we would call it the numerator. If we see 0 in the numerator, just like we see 0 divided by anything, boom, is going to be 0. So we saw examples like this on that last exam. 0, if it's in the numerator like it is right here, automatically your answer is 0. Now the reason that is, so let's look at an example. So if I did 0 divided by 10, okay, so in long division, you'd have nothing to divide with 10 people. Now this long division that I've written, we would say, look, if you got nothing, how many times does 10 go to 0? Or if you had nothing to divide with 10 people, how much is each person going to get? They're going to get nothing. That's why that's 0 right there. And the same is true, well, it's kind of true on this one. It's just a little different. These are undefined on the assignment, or on the exam rather. We saw this as D and E. Does not exist. It's just undefined, which mathematically, I mean, you can get really nerdy about undefined, but I'm not going to go into that. But here's why this works. Why it is undefined, we would say. So let's look at, let's do 3 divided by 0, okay? Now, let's say, so this means that you have 3 of something, and you're going to divide it into nothings. So the question this is asking right here is, how much of nothing is in 3? Which sounds kind of weird. But there's an infinite amount of nothing in 3, which sounds really weird. But that's why we call this undefined, but we're looking at this more as a D&E situation. So my infinite symbol just kind of looks like an 8 on its side, but whatever. But again, if you think about this, how much of nothing is in 3? Hopefully that makes sense. There's an infinite amount of nothing in 3. When you compare fractions, it will be crucial to make the denominators the same. Now, why do we need the denominators the same? It's because if you make the denominators the same, you will now be comparing the same size pieces. After you have the same size pieces, then you can compare the numerator, because that tells you how much of it you have. So, if you have a pizza cut into fourths, which one is more, 5/4 or 3/4? Well, 5/4 is, of course, right? And so this is the importance of making the denominators the same. We're going to see this again, though, the denominators, forcing the denominators to match once we get into addition and subtraction of fractions, too. So in the end, once we get those denominators the same, it's a direct comparison of just the numerators. You don't even have to compare the denominators anymore. So we look at these two examples. We got 7/11 and 1/2. Compare the two fractions by choosing the correct symbol and place between them. That's less than, greater than, or equal to. So they're not the same size pieces on this. I got a pizza that's been cut into 2 pieces, and I got another pizza that's cut into 11 pieces. What the heck? So what we're going to do is force the denominators to match. Here's how we force denominators to match, which I think I saw on the exam last time. But what I'm going to do is I'm going to take this 11 denominator, I'm going to multiply it into the denominator of the second fraction. But again, if I do it to the denominator, I've got to do it to the numerator as well. Now, doing this it's going to force the denominators to match, so we're comparing the same size pieces.
Oh, so this is, we're adding?
No, not yet. No, we're comparing. We're comparing right now. Now, in the denominator, 2 times 11 is 22. In the numerator, 1 times 11 is 11. Okay, now that's that second fraction. This means that the first fraction should also have matching denominator of 22. How do I get that? Well, I take the denominator in the second fraction and multiply it into the denominator of the first, but also the numerator. So 2 times 11 is still 22, but in the numerator, 2 times 7 is 14. Now, the sizes are the same size, pieces, that's the 22nds in the denominators. But I have 14 and 11, and I know that 14 is bigger than 11, which means that in between the two original fractions, 7/11 is bigger than 1/2. Now, here's the thing. So let's go back on this. So if I were to compare these two fractions, but let's make the 7/11 a negative. In fact, let's go one step further and make the 1/2 also a negative right here, because we got to be able to compare negatives as well. So when comparing negatives, which we went over, I think, in Module 3, remember, the more negative it is, the less value it has. It's like, you want more dead or you want less dead? I'd like less dead. So I want those numbers to be smaller when I'm looking at negatives. Now we know the comparison is already going to be 14 over 22, but now negative. And then it's also going to be 11 over 22, but now negative, right? Yep. Now, and I'm going to take this one step further. We're only comparing the numerators, negative 14 and negative 11. We got to choose which one, again, bigger, or you could say smaller. But negative 14, since it's more dead, or you could look at it on a number line. So this is where 0 is. You'd have negative 11 here, and the negative 14 about right there. Negative 11 is to the left of negative 14. However you want to look at it, negative 11 is bigger than negative 14, or negative 14. This reads negative 14 is less than negative 11, which means that negative 14 20-seconds is less than negative 11 20-seconds, which means negative 7/11 is less than negative 1/2. Remember, the difference here is that we were comparing positives before, which is why I was eating the 44 20-seconds. Now that we're comparing negatives, we want the smaller of the two negatives. Now, on the other hand, if this was a positive 1/2, it would still be eating to the right here, because a positive is always bigger than a negative. So just be aware, make your denominators the same, and then make your comparison of the numerators. And that's it. So again, we've seen that we should be able to change fractions between mixed numbers and improper fractions in both directions. And then we should also be able to simplify and then compare fractions. Yeah, some of those fractions were kind of nasty looking with letters and exponents and stuff, but we saw how to do that.